Thank you for joining me. I'm going to try to do number 58, which I had a problem with in period 4, but I want to correct that at this point. Number 58 reads, a car goes around a curve on a road that is banked at an angle of 33.5 degrees. Even though the road is slick, the car will stay on the road without any friction between its tires and the road when its speed is 22.7 meters per second. What is the radius of the curve? Okay, first of all, we have a banked incline. We have an angle of 33.5 degrees. The car is going to stay right here, even though it's either coming at us or going into the paper. Either way doesn't matter. First thing we need to decide is which way is X. I'm going to point X in towards the left. I know that's a little bit opposite of what we usually do, but X is going to be horizontal, Y is going to be vertical. And the reason I want X to go in that direction is that's the direction that we're going to have an acceleration. We have, of course, a weight going in this direction, and we have a normal force going in this direction. All right. In the X direction, that's the direction in which we have that's the direction in which we, of course, have a net force. If we did the whole parallelogram rule thing, we would get that there is an inward force on this car that goes this way, which is really just the X component of the normal force. Now, we do not know what the normal force is because they did not give us the mass of the car. What we do know is that the X component of this normal force, and of course, this is up here, the 33.5 degree angle. We know that the X component of that is going to do the accelerating. Now we're going to need the normal force. Actually, if we were to look at our centripetal force equation, the centripetal force is equal to the mass times velocity squared divided by the radius. Our centripetal force, we have decided, is going to be the X component of the normal force. That means we need the normal force. So we're going to turn to the Y direction. In the X direction, it accelerates. In the Y direction, it is absolutely not accelerating, it is in equilibrium. That means that this here, which is the component of the normal force in the Y direction, this is the normal force in the X direction. The normal force in the Y direction is, of course, equal to the weight. The weight is equal to the normal force in the Y direction. The weight is equal to the mass times gravity. The normal force in the Y direction is going to be equal to the normal force. This is the same as this side here, which is the adjacent side to my 33.5 degrees. So that is going to be the cosine of my angle. So that means that N is equal to mass times gravity divided by the cosine of my angle. Now that I want to put that back into here, we're going to take this one and we're going to take this one. We're going to combine them up. And we're going to say that my normal force, which is mg divided by cosine theta, gets multiplied by the sine of the angle, because I want only the X component of that normal force. And this is, of course, equal to the mass times v squared divided by r. Now, hopefully you can see a few things. One is that the mass cancels out on both sides, and that we have sine over cosine. So we've got g tangent theta is equal to v squared over r. We are trying to solve for r. R is going to go up here. This stuff's going to go down there. We end up with a formula of r is equal to v squared, which we have, divided by g, which we know, multiplied by the tangent of theta, which we know. This is going to give us a final answer. That final answer, after we plug in the values, ends up being 79.4 meters. Okay, and that is it. Thank you for watching with us.